Hello and welcome back to my channel. This is Moshix, and before we go into the assist assembler for our beloved MVS 3.8, I just want to make a brief announcement that I'll be moving tomorrow, and such I'll be a little bit less available for making new videos for the next couple of weeks. It may be well into late September before the next video comes out, but I have several projects I'm working on for videos for MVS 3.8 as well as for DOS VS and some MVS 370 stuff that I'm working on. So I'll be, even though no new videos will be coming out for the next 2-3 weeks, I'll be making those videos while I'll be traveling and moving. So today we're going to be looking at the assist assembler. Now the assist assembler, let's go here into incognito, is an assembler that was written in the 70s by the Penn State University, and it's, in my view, the best way to learn S370 assembler for a very simple reason. The assist assembler is not a normal assembler in the sense that you feed it a source code and and then it will translate into machine language that you can run on MVS. Rather, it is a learning tool. So Penn State U assist assembler, if you search in Google like this, you should get Penn State, I just call it the PSU assist assembler. Let's see what Google gives us. Yeah, so there is a little page here on Wiki. Assist is the assembler system for student instruction and systems teaching. So it's an S370 compatible assembler, but it's really an interpreter. What this means is that when you give it S370 assembler, it will not actually be run by MVS, it will be run by the assist assembler, which is an interpreter and interprets the assembler. And by interpreting, you can actually get much more diagnostics data, as well as more hints as what is wrong with your assembler program, and that's why it's such a great way to learn assembler. Also, feeding it data and getting the input and output out of your assembler programs will be all self-contained within the assist assembler. You don't actually have to resort to JCL. It sounds a little bit strange, and and all this is in batch, obviously. So from today's point of view, where everything is interactive and everything is inside the web browser, this sounds all a little bit strange. But back then, this was innovation in the 70s, to have an assembler that's actually an interpreter, so you could learn to assemble, to code in assembler, was a very useful way. There are some links here. We can go here. Yeah. If you land on this page, you're going to have a very good manual on how this all works. And obviously, it is beyond the scope of today's video to learn how to use. First of all, how to code in S370 assembler. That's why we're showing this video, so you can use this tool, but also all the capabilities of this tool, the assist assembler, there's so many tools in there. It's just beyond the scope of today's video to learn them all. But there's a very good manual. Now, instead of spending time on this page here, what we'll do is I just downloaded a fresh new copy of TK4, and it's in here. I just freshly unzipped it, and So why don't we just start that? Make this window a little bit bigger. And I made the fonts a little bigger for some of the people here who have in the past rightly said that the fonts are too small to read on small devices. So I use speaker fonts here. So let's connect to this instance. And as you can see here, this is running on my Linux machine, even though I'm recording this on Windows. Machine where all this is running is my tiny little Dell XPS laptop next to my computer here, so I can keep an eye on it. Yeah, so this has come up. Now, if there's actually an assist assembler already installed in here, standard initial password, I'll actually go and change it if you allow me, so that it's going to be easier to code in the JCL, which we will require to do. So let me just change it. Sorry guys, logged off, HERC01, and then we give it the TK4 supply password, and I'll change the password to HERC01. Oh, we cannot use the same password, so let's just call it YouTube. What is going on here? Okay. What? I'm some strange. Okay. Okay, so it seems to be HERC01 is the password. Okay, so we got that set. So this is a fresh install. Sorry about this, guys. Yeah, we have here a bunch of messages related to invalid access attempts, but I think I figured it out. Anyway, so this is, and there is, in fact, as I was saying, there is already an assist assembler installed, but it's not installed the way I like to have it installed. And so if you go here to 3.4 and you do sys2 PSU for Penn State University, where the assist assembler was developed, you'll see that it's actually already in here. We even have the manual. It's all in here. So the only thing is there is no procedure for it. So we would have to create procedures and all that so that we could easily run it. Not that it's terribly hard, and most of you people would know how to do this, and everything is in here. The object code is in here. Everything is in this PDS. However, you can see here. No, this is link modules, but it's all in here. So, however, I find this not the best way to use it, and luckily, if we go back to our browser, Jay Mosley has a very easy installation procedure to install the assist assembler. I've been referring to Jay Mosley's website quite a bit. I do recommend you spend time there, because there's an endless stream of interesting things to do there. So Jay Mosley has here a full installation procedure to install assist, so that it goes into the proclib, and it becomes very easy then to call the proclib and use the assist assembler. So He has here an installation archive, which I've already downloaded, assist.tjz. And what you do is you download this. Okay, let's assume you've already all done that. And I'm going to make this window a little bit smaller here, so we can use this one, which has slightly bigger font. If you go to, well, actually, it's in my download section. Yeah, here it is. So what I do is I copy the assist assembler into MVS, to my MVS directory and to the JCL directory here. And here it is. So now, at this point, it's really quite easy. What we do is we unzip and then we untar it. Okay, and obviously creates a JCL subdirectory here in this case. We go in there, and there is one installation job and then several test jobs. The good thing about this approach to install the assist assembler is that it compiles the assist assembler freshly on our system, which is my preferred way to go about this. So let's go and look at this job. Obviously I have my color clock coding here. We would have to start to adapt this job a little bit. I'll call it HERC 01A. I want this to go to class H, but since we're running, I will be running this from the card reader. So remember that because of our REC-F, look here, you know, we have REC-F protection. We have to actually, so since we're supplying this from outside TSO, we have to give it a user equals HERC1, password equals HERC01. Just the password I gave it when we changed it here on initial login. This will allow it to execute. We can also just have a little bit of a view at this. Let me make this window bigger. So that's the full job, and what it does is it copies itself into our MVS and then assembles itself, so that we create the assist assembler from this assembled source code. Obviously there's quite a bit here. There's 31,000 lines of JCL. Talk about a big JCL job here, but this is nothing for my little laptop here. My laptop has I don't remember how many cores, but yeah, 4 cores, and if I'm not mistaken, 16 gigabytes of RAM or 8 gigabytes of RAM. Not too sure, but plenty for what we need to do. So now that we adapted this job and gave it the user and password, which is very important because otherwise, you know, this job will not run properly. Let's make this window a little bigger, and let's try to execute it. We'll do a device init. 00C is our card reader. JCL assist. Yep, this is our installation program, and this shouldn't take much more than a second, even though, as we saw, it's 31 or 61,000. I don't remember. Let's count the lines here. Yeah, assist. Yeah, 31,000 lines. But this shouldn't take much longer than a second or so. We can keep an eye here on the CPU usage and obviously on the MIPS counter and the IO counter here. But it really, I don't think this is anything that will make our MVS or my laptop sweat. Yeah, you can see here it's running, and the good thing is that Hercules is very well multi-threaded, but something is not quite wrong. The invalid password. I still don't have the right password here. So let me, Herc01. What is the password for this job? Oh, it's Moshix. Okay. Alright, so sorry about this, guys. I should have done this maybe before starting this video, but it's not a big thing to change. Okay. Okay, that should do it now. Again, let's go into, and let's just rerun this job, and let's keep a good eye here on what's going on here, and we should see the MIPS, the CPU, the real CPU usage on the laptop go up here in this window. And nothing, of course, is going to happen at all in this window here in the terminal window. It's all going to be in here. So let's start it. Yeah, this time it accepted it, and we can see that one thread here is using quite a bit of CPU time. But as far as I can see, this job already ended. So this wasn't more than a second or two. I didn't count more than 2 or 3 seconds here at all. Let's go in here, and this was job number 2, because job number 1 is the one that failed because that password makes sense. Let's go and let's check the output here. That would be okay. So obviously, as we always do, is we check the return codes. These are all zero. So it looks like it installed. Do the run this job. Okay, so let's check here what happened. There's many steps in this job. I think I counted them in the past. There were something like 20 or 30 job steps. This is still just copying stuff over, and then there is an assembler step. I mean, there's over 10,000 lines of output here. We're not going to go through every line here. Just want to get to the interesting stuff. Let's scroll 500 lines at a time. Okay. Still not getting anywhere. I mean, this is obviously a big program because it has to emulate the whole S370 computer. So in a way, what's really happening is once you run the assist assembler, is you're emulating an S370, I think, model 158 processor or mainframe inside MVS, which itself is running on top of the Hercules machine on top of Linux. And you'll see that the performance is actually still many times faster than a real mainframe back in those days, because modern CPUs are just so fast. Okay, this is still all just the assembler code for the assist assembler, but it compiled fine. I didn't see any errors. So let's go to the bottom, and So, I mean, this all went well. That's all we need to know. You will be able to browse the output from this giant job at your own leisure. This is obviously the one that didn't go through. Because of the first one that we tried, we can purge this, and it's gone. And now what we can do is, now that we can actually test it. And how do we test it? Let's go back to this session here. The Penn State University team has provided several test utilities. Let's try the first one. Again, remember, we will always have to go and change so that we can give it the password. T for test. I want to put it class A. Oops. And I want to make it message class H, followed by the user equals 01, password equals Moshix. Without this is not going to run, guys. So, but now we can immediately see a very good example of an assist job. So we execute the assist assembler here. It's just called assist. And then there's a job card. So since the assist assembler is an interpreter, it has its own little language. So you tell it this job is called assist. And then we have a little assembler program here with a macro definition. So you can use, it is quite compatible with the normal assembler. I would say it's 99% compatible. You can do macros. There's just a few things you can't do, which are relate to relative addressing, but you could do most of the stuff, and I have done most of the stuff. And the assist assembler also provides some very cool macros on its own, like xread, read card. You don't actually have to do the whole get and put with QSAM. It has very nice macros for that. Also for decimal conversion, those are very well known, and I use them even in my normal assembler. And here is some data, and then dollar entry is a command to assist to start after compiling this above program to start it, and here's the data below. So we can, now that we've given it proper user and password, there's no reason why we shouldn't be able to test this. And let's just, what is it called? S test 0. Yeah, and obviously this is all very fast. If you go here, we should see our new job. Warning messages for, oh yeah, obviously I didn't, the user ID was wrong. There's an R missing. Sorry, I don't know what's going on with my spelling today. Let's start this again. And it's done, and we should see it here. And in fact, it is here. And yes, so we have return code 0. We did execute it, and so immediately you see this is a different assembler than the XF assembler supplied with our TK4, which is the XF assembler. A very, very good assembler, but this is a learning assembler. So first of all, we see that we compiled this today. Today is the 4th of September, 8 o'clock in the morning. So as you can see, we have a freshly compiled assembler 4.0, assist assembler 4.0, and it's emulating, so it's not emulating a 370 158, it's in fact emulating a 370 model 65 for OSVS, MVS. I mean, talk about nostalgia and seeing beautiful things. I mean, this program was written in the 70s. If you go look at the source code, I think it was written in 71, 72, or possibly 74, and it still runs beautiful. And we could run this job on a modern operating system such as ZOS 2.2 just the same. It would work just the same. And there's no reason why you wouldn't use the assist assembler for teaching your people. If you run a real ZOS in production and you want to teach your people assembler, you could still use this job and execute it on your ZOS and would run just exactly the same. I don't think that the high-level assembler would assemble this any differently than the XF assembler into an object, a load module for the assist. Should run just the same. And then so we fed it a little assembly program here with a macro definition. That's what we looked at before. All here, and then it starts to assemble it. Here just looks just like a normal assembler output here, and once it's assembled, it tells us some stuff that, for instance, our normal XF assembler would not be able to tell us because it's not an interpreter, it's just an assembler. So assembly time was 6,000ths of a second. It assembled at a speed of about 26,000 instructions per second, and that's not bad at all. And then it executed the load module, and we have some diagnostics here about the execution of it, and executed it in 1,000ths of a second, 617 instructions executed in that time. That's an execution speed of about 617,000 instructions per second. Now, if you go and consider that, as far as I have seen, to properly emulate the S370 architecture, you'd need about 100 instructions for every S370 instruction, and then that's for the assist assembler, and then Hercules has to do the same thing. So it's if you use the calculator here, it's 617,000 times 10,000, because it's 2 times 1:100 ratio, right? That would be an execution speed of, let's count the zeros here, 6.17 GIPS, or 6.1 billion instructions per second. That's the execution speed of this thing here on my little laptop. It's just amazing. This is one test. We can happily do another test to do more complex stuff. Let's look at test AS test 04. Again, we'll have to go and adapt, put in here, let's put in T, KS, U, so we can keep them apart in the spooler. I want to give it class A, and I want to put it in message class H, followed by a comma, and then as usual, her 01, password equals moshix. Oops. And then let's see what this does as a new macro. Some macro definitions here. I have not really looked at this before, but this looks like very advanced macros here. Okay, and here we have the real assembler. Just trying to understand what it's doing. It's testing macros. I mean, this would be advanced macros even for the XF assembler. I think they're trying to show us how good this assembler is and how close it is to the XF assembler. Okay. There's a lot of warnings here. This may actually be so advanced that it won't be able to run properly. And it's actually also quite a big job. Let me see how big this is. it's 6,000 lines of assembler, more or less. So why not? Let's give it a try. This was AS test 04. Okay. Let's see what happens. I mean, you know, that's the beauty of it. This is all so easy to go and change. So let's run this. And it's already ended. I mean, I'm always surprised how fast this is. A job of this magnitude, when I was working with real mainframes in the early 80s, a job with 6,000 lines of assembler, I mean, I would have to wait. You know, I remember my machines we're working on back then was a 3083BX with 16 megabytes of RAM, 1 CPU, production, test and development all in the same machine, about 100 TSO programmers and about 3,000 Kix users all on the same machine. I would send a job like this for assembly. I would probably send it and wait, I would say, a good 5 to 8 minutes to get this message here, job ended. I mean, because the machine was constantly at 100%. And guess what? Nowadays, when people see a machine and it's running at 90% or even at 40%, as they go complain to bosses and say, "Oh, our machine is running 50%. We need to get a more powerful machine." Well, back then I was in the military. People said, "Well, we bought the machine to run it on 100%. We didn't spend millions to run it at 30%." So running a mainframe at 100% was a desirable target, and nobody was complaining about it. But I would have to wait probably a good 5 to 8 minutes to get this job through, and then I will go into SDSF, which I do miss quite a bit, and in our TK4 and MVS 3.8, because it is a very good spool viewer. But here it is. Let's go look at our job. This was job number 5, so we're good. This is it. And so it ran fine actually. So the return code 0, and this was all executed fine. Again, this is our own assist assembler, compiled a couple of minutes ago, emulating an IBM 370 Model 65, which was a medium-sized mainframe back in those days. Maybe not the biggest, but also not a low end. And let's see what it does here. Yep, it's compiling all this, no errors. Okay, so there's multiple compile jobs in here, compiling once to 30,000 statements per second. And here compiling at 41,000. So it's compiling several modules and then probably linking them together. And so let's see what it says here. Okay, this all went through fine, and I guess the execution is at the very end. So let's go to the end. I mean, I don't know what this job does in detail. But it looks like it did it all just fine. So no errors whatsoever. It's pointing out here to some syntax errors here. Oh, but these are the actual error message definitions themselves in the data definition. So no, this is not an error message. So I mean, you can see this is just normal assembler. There's load address 41, load 58. I mean, I recognize the codes because I'm doing a lot of assembler programming, so I recognize all the machine codes for the assembler statements. In the XF assembler and in MVS, alignment is still an issue. So certain things have to be aligned on 4 bytes boundaries, or sometimes on 8 bytes boundaries, and so the proper alignment is something that you do still have to pay attention to. Later mainframes recover much better from alignment issues because of the way that RAM was addressed. Back in the days, RAM modules were addressed always at RAM frame at a time. It's really complicated concept to explain here without using graphics, but certain assembler code had to be aligned on certain memory boundaries, and sometimes you would have to put in an alignment statement like this one here. But with later mainframes, which use much finer grained memory access, and with the high-level assembler that you would use in today's ZOS operating system, alignment issues have been greatly reduced. Not totally, I think. I've seen 1 or 2 cases where I had to align, especially with very old code, but alignment is not so much of an issue. But back then, yes, you did have to take care of alignment. So anyway, so I think we've tested everything here. We've shown how to obtain the assist assembler source code, put it into our MVS, have it compiled, assembled on MVS, and then all our tests have executed fine. And from this point on, you could start reading the manual, RTFM, obviously, if you allow me, and start learning assembler. I think one of the fascinating things about the mainframe and about MVS 3.8 is the assembler. I think it's one of the easiest assemblers to learn. It's far easier than the x86 assembler. Or any other assembler I've seen. It's very elegant, and it's almost like a high-level language. So I mean, there's no reason not to learn the assembler. It's a lot of fun, and wouldn't anybody be able to say, yes, I know how to program the assembler? How many people out there today who do JavaScript and such high-level languages that I've seen things where one JavaScript statement turns into millions and millions of machine code lines. That's how the high-level languages are today. But knowing what's happening at the lowest level, at the machine level, is still useful, and there's still going to be a job for people who know how computers actually work. So I think learning an assembler is a very useful thing, and I'm certainly, my kids are learning assembler. My youngest started learning assembler at the age of 9, so there's no reason that we all shouldn't learn this S3 semi assembler. That's it for today. I think we've shown enough, and as I said, I'll be reporting back in a couple of weeks. And thank you for watching, guys, and subscribe to my channel if you like my videos so you get notified of future videos. If you like this particular video, please do press the like button, and see you soon. Thank you very much. Goodbye.